second session. In second session, I'm going to give you a few more definitions which will be important for studying the algebraic structure like group, ring, and field. Now, to begin with, probably you have, and all of us know that when we deal with equations like of this form, when we write that x plus 2 is equal to y plus 2 like this, we have done it in school. We are in the habit of cancelling this thing, and we write, if this is so, then this implies x equal to y. Also, we are in the habit of doing this kind of thing, that when minus 1 plus x is equal to minus 1 plus z, then we also call that, yeah, then let us cancel it, and this implies x equal to z. So we do this kind of thing. We have done this kind of thing in school. But these things, although they are taught in school, in higher mathematics, these are very absurd. These are actually not done in this particular manner. In higher mathematics, in actual case, they have some sort of characteristics, and in a special way, we actually try to treat them. So these old methodologies will no longer be helpful or should not be used any further. So here I'm in the light of that, here I'm going to explain this from a general perspective. Okay. So with reference to my earlier session, where I gave you 5 definitions related to binary operation, I am writing here definition 6 because this session 2 is the continuation of the last session. Okay, and now this time I have not forgotten to play the record button. So this particular session is also getting recorded. Now, a binary operation star on a non-empty set, binary operation star on a non-empty set, capital A, is called left cancellation is called left cancellation, or not cancellation, it's called left cancellative, or called left cancellative, or is said to satisfy, left cancellation law if for any A, B, C belonging to A, A, B, C belonging to A star B is equal to A star C. And this implies B is equal to, my B looks like 8. B is equal to C. Now I am not cancelling A from the left hand side. No, I'm not doing this kind of thing. Remember, see, I'm not writing A cancels and A cancelling each other. This kind of thing you shouldn't write. Okay, everybody can see what is happening. So A star B equal to A star C, and we are writing B equal to C. You may ask me, sir, why can't we cancel them? What is the problem? Everybody can see that we can cancel it, and we are in the habit of canceling the thing. So why can't we do so? So let me explain that particular thing from a simple example. Say, for example, when I wrote that x plus, sorry, when I wrote that say for example, I'm solving this equation, x plus 2 equal to y plus 2. If you ask me to solve this equation, then I'll say that, okay, what type of, I cannot solve it immediately, because I have to first of all know that these elements x and y, to which particular set they belong. Are they rational numbers, or are they real numbers, or are they natural numbers? For example, if I give you the set capital N, which is a set of natural number, and I ask you to solve this system, suppose a child has been taught that only number system which is available is the natural number system, and he has been given to solve this, and you know how to solve it, then what will he do? He will be confused. He will do that. He will divide both the side by the quantity 2, and he will write it as x equal to 3 by 2, but he will not be able to identify what is 3 by 2, because you haven't taught him that such kind of fractions also exist in nature. So here, when we are actually, you are here, you have given me the problem that to solve x plus 2 equal to y plus 2, you just can't cancel it. We don't cancel. What we do, we first try to know the system. Suppose you are dealing with the system of natural number, then this I cannot solve it. If I say that x and y is a natural number, you cannot cancel 2. Why? Suppose you have given me the set of integers. You say that small x and small y these are integers. Well, then I'll say, oh, okay, then you can write it as x plus 2 plus minus 2 and y plus 2 plus minus 2. And then you know that set of integers with respect to addition is associative, and therefore it is a semi-group. Then immediately you can say that, and it is also monoid, so it has the identity element in itself, in it. So you can associate these two numbers together. Let me erase this portion. You can associate these numbers in this manner, because things can be associated, and you can associate these things in this way. And then you will write that, okay, 2 plus minus 2 is 0, and 0 belongs to the set Z, and y plus 2 plus minus 2 is 0. And then you know that x plus, since 0 is the identity, so you will write, okay, then x plus 0 is x and y plus 0 is y. And therefore, actually, we do all these operations. We do all these operations in our mind, in the back of our mind. And ultimately, we write that, okay, in this manner, we get x equal to y. But what we are taught, instead of doing all these things, what we are taught, because we are not taught what is associative, what is commutative in that sense. People in school, they like to solve equations, but they don't know what sort of equation they are solving. So I also, as a student, school student, I also did the same thing that you have done. Because don't think that now sir is telling this kind of thing. What did he do when he was a student? I also, as a student, faced the similar situation that you faced. But after that, when I was in the higher mathematics, when I was studying higher mathematics, then I also, just like you, I also came to know that actually what is happening. So in school, we are taught that, okay, you don't have to do all these things, you just cancel 2 and 2. So this happens for the addition. Now, if you talk about binary operation, this happens for, if it can happen for any binary operation. If it happens for any binary operation, if it happens for any binary operation, then such a binary operation is said to follow the left cancellation law. This property is called the left cancellation law. And similarly, the thing which I have shown you here on the right hand side is not actually left cancellative. You can very well see, because in the left cancellative, we have to keep the same number on the left of the equation on both the sides. This is actually what you can say that it is right cancellative. So similarly, star is called right cancellative, is called right cancellative or is said to satisfy the right cancellation law, the right cancellation law if for any A, B, C belonging to capital A, B star A is equal to C star A implies B equal to C. So just look at this. Just look at this. This is the left cancellative thing, and this is the right cancellative thing. Don't forget this definition. I can see 63 participants in this session, but only 27 participants have written their, put their attendance. Others, please do so. Now, if a binary operation star is both left and right cancellative, both left and right cancellative, then it is called cancellative or is said to satisfy cancellation law. In general, okay? Okay. Now, I hope that you have understood what do we mean by left cancellative and right cancellative. The next definition which I'm going to write is goes like this. So I'm starting from here. This is definition 7. So this definition is also very important for group theory. Let capital A, comma star be a mathematical system. And now you know what do we mean by mathematical system. I've already explained to you. So let A star be a mathematical system. An element E1 belongs to A is called a left identity, is called a left identity of A comma star if for all x belongs to A, if for all x belongs to A, E1 star x is equal to x. E1 star x equal to x. This is called left identity. Okay. When the element is getting multiplied with x from the left hand side only, then you get small x. Otherwise, if you multiply this term from the right hand side, then you may not get x. Such things may appear in the system. So if this happens only, then we only call it as left identity. Remember the term, left identity. Similarly, an element E2 belonging to capital A is called right identity of A star if for all x belongs to A, just the opposite, x star E2 must be equal to x. Okay, an identity is both left and right identity. When we talk about identity element, we have to understand that it is both left identity and right identity. Okay, that is E belonging to capital A is called an identity of A star if for all x belongs to A, E star x star E is equal to x. Okay, and in general, since to save our time, you may find in some books that they are writing in this manner only: ex equal to xe equal to x. Do not think that in between e and x multiplication dot is present. We are in the habit of writing AB in place of A into B. It is not the case over here. You have to understand what sort of binary operation is present in between the two elements. So be careful about that. And also be careful about this term. Then when I am writing E2 belonging to A, when I am writing E belonging to A, and when I am writing E1 belonging to A, because you cannot say that 0 is the identity, left or right, or just an identity of the natural number set, because 0 is not present in the natural set of natural numbers. Okay, so you cannot say but that it is the identity of that. You can say that 0 is the identity of all the set of identity of the set of positive integers, but you cannot say 0 is the identity of the set of natural numbers. Because of these things, there's to be an identity, left or right or both, the identity element must be an element of the set under consideration. That is the fundamental requirement. Okay, so be very careful about this. Now I am going to prove a very simple theorem. It looks very simple, but it's also very important. Okay, so an identity, the theorem goes like that: an identity element of a mathematical system, A star, if exists, this is very important, if exists, is unique. Okay, now what is the proof? The proof is very simple. You just follow the logic what I am writing over here. Let E1 and E2 be the identities of the mathematical system A star. Since E is an identity, E star x is equal to x for all x belonging to A. You could have also written that E star x equal to x, and since E is an identity, you could have also written that is x star E equal to E. So I have written only this because in the case of identity, you can write this or that. They are same thing. Okay. In particular, now look at this particular logic, what I'm writing right now. In particular, E2 is also one such element of capital A, because I have written that since E is the identity, so E star X equal to X. And what is X? X is any element. It is happening for all element of A. So E2, the element, it is the identity, and therefore, since it is an identity, it, as I have told you, that this identity must be a member of the set capital A. So in all possible values of X, E2 is one such value. So since E2 is also one such element of capital A, so E1 star E2, that is also equal to E2. Okay. Again, since E2 is an identity of capital A, so X star E2 is equal to X for all X belonging to capital A. Just look at this thing. Here I have written it in the form of left identity. This should be E1, not EU. This should be E1. So I have written this in terms of left identity, and here just I have made a trick. I have written this in terms of right identity, because I am allowed to do this. I am allowed to do both of these because they are identities. So X star E2 is equal to X for all X belonging to A. And since E1 is one such element of A, so E1 star E2 is equal to E1. Okay, just look at this. What have we got? E1 star E2 equal to E2, and E1 star this is E1 star E2 equal to E2, and here I have got E1 star E2 equal to E1. So you can call this as number 1, and you can call this as number 2. And from 1 and 2, we write E1 is equal to E2. That is, the identity is unique. Identity is unique. First of all, identity must be present in the set. That you have to justify. That the identity you are talking about, this must be in the set. Then if this identity is there, then that identity is actually unique. And this is not happening only for the mathematical system of the form A star. It can happen also for the mathematical system like vector space and ring and field everywhere. Any mathematical system, this may happen. Therefore, in the last class, I was so interested in finding, you tried to find whether a system is a group or not. Very good. But also I tried to find what is the identity element over there, because there cannot be two identity elements in a particular group. Identity elements, if exists, they always must be this identity element should always be unique. Okay, so therefore in abstract algebra, when we study group, we try to find the identity elements and the inverse elements and so on. So you can write, if you're writing, then you copy this particular thing, or you can take a snapshot of that. I'm going to the next page, and I'm moving back to my discussion on the study of group. Okay. Let G star be a group. Let G star be a group. Number one, for all A belonging to G, A inverse is equal to A inverse of inverse equal to A. Okay. And number two, I'm writing here. And number two is for all A comma B belonging to G, A star B inverse is equal to B inverse star A inverse. B inverse star A inverse. Now, what is inverse? When we talk about, in the last class, I told you that if for all A belonging to G, there exists an element A prime in G such that A star A prime is equal to E. A prime is the inverse element of A. Is the inverse element of A. And this inverse is often denoted by, this is the notation. This doesn't mean A to the power minus 1. Don't think this as A to the power minus 1. Remember, this is not A to the power minus 1, or do not try to write it as 1 by A. Don't think that this is 1 by A. It is not. It is just a notation. Treat this inverse as a notation only. Okay? So I'm going to prove it. These two theorems I'm going to prove right now. Remember, I'm writing it over here. This is page number 3, I think, page number 3. A inverse, this is a notation only. Okay. So in a group, we know that each element has a unique inverse. Now, just like, okay, I have to say something about this. You know the definition of inverse. I have told you that this identity element, if exists, is unique. So if I must write one thing, try to prove that inverse of an element, if exists, is also unique. Try to prove that the inverse of an element, if exists, do it by yourself. Do it by yourself. Okay, I'm not showing it. So therefore, I have written here that in a group, we know that each element has a unique inverse. Hence, for A belonging to G, A inverse has a unique inverse in G, and we denote this by A inverse. Now A is any element. If any element, for any element, the inverse of the element exists in a group, we know, and this inverse is unique. Now for A belonging to G, if A inverse is the inverse of A, then A inverse can also be called the element of G, because the inverse element is also present inside G. Now, if this is the element which is present inside G, and since every element of G has unique inverse, so A inverse will also have inverse, and that we are denoting by A inverse inverse. Now, try to follow the logic. Now, A inverse star A is equal to A star A inverse is equal to E, implies that A inverse implies that A is the inverse of A inverse. A is the inverse of A inverse, because you know, try to consider, I mean, if you are not following this, try to imagine in place of A inverse, try to imagine A, and in place of A, try to imagine A prime. And see, the same thing is happening. So A prime is the inverse of A. Here A prime is equal to A and A is equal to A inverse. And therefore I have written this thing. Try to imagine this. So A is the inverse of A. And since the inverse of A inverse is unique, which comes by the property, we must have A is equal to A inverse, which proves my first result. The second result, number 2, let A comma B belonging to G. Okay. Now I'm writing A star B. Let us multiply this. Let us operate B inverse A inverse, B inverse star A inverse, and let us take a binary composition of these two terms, and let's see what is happening. Okay, this you can say a trick. I'm actually making over here. This is a trick. So I am taking B inverse, I am taking A inverse, I am considering their binary composition, and this binary composition is being composed with A star B. Now, after that, what I can do, I can apply the associativity property over here, and I can write it in this manner, that this term and that term has been taken together. After this, what I can do, I can associate these two terms together, and we can write it in this manner. But we know that B star B inverse is E, so I can write it as A star E star A inverse, and A star E can be written as A star A inverse, and this can be written as E. So we have got A star B inverse star inverse equal to E. And similarly, page 4, similarly, B inverse star A inverse star A star B is equal to E. That can also be shown. Hence, B inverse star A inverse is an inverse of A star B, since the inverse of an element is unique. Inverse of an element is unique in a group and since A star B inverse denotes the inverse of A star B, it follows that A star B inverse is equal to B inverse star A inverse, and that proves the result. Now I know that probably you are not so comfortable with this kind of proofs, because this requires so many lines to be written. This requires so many logic to be remembered. This requires so many energy to be involved to solve this kind of problems. But in abstract algebra, the problems will be of this form. It will not be possible for me to solve each and every problem or theorems for you. So I shall recommend you to take a book and you can study the theorems, the problems. You can study the theorems, various other theorems are there, which you can do by yourself. I am writing, I'm giving you another theorem which you try to do by yourself. And if you can't, then you can later ask me. The statement of the theorem is for all A, B, C belonging to G, if either A star C is equal to B star C, or C star A equal to C star B, then A equals to B. This you can prove. This is talking about the left cancellation and right cancellation law, and also try to prove that for all AB belonging to G, the equations A star X is equal to B and Y star A is equal to B have unique solutions in G for X and Y. Proof. Please rejoin after this class ends.